Hello everyone. Today I am going to discuss elastic constant, true stress, true strain, engineering stress and engineering strain of the chapter simple stress and strain. Also at the last I will discuss about the total elongation developed in a body. So in the last lecture we discussed about the Hooke's law. So what is that Hooke's law? According to Hooke's law, the stress is directly proportional to strain. So that means stress is equal to some constant multiplied by strain. And that constant is known as elastic constant. So if I want to define the elastic constant, then elastic constant is the ratio of stress upon strain. Now there are three types of elastic constant. The first one is modulus of elasticity, or we can say it is Young's modulus. So Young's modulus is defined as the ratio of linear strain upon linear stress upon linear strain. It is defined as the ratio of linear or longitudinal stress, and linear and longitudinal stress we already discussed in my last video. To the linear strain, it is denoted by E. So we can say E is equal to linear stress upon linear strain. Then bulk modulus. Bulk modulus is defined as the ratio of normal stress. Now this normal stress may be compressive stress, may be tensile stress, to the volumetric strain. Now, what is volumetric strain? Volumetric strain is change in volume upon original volume, and it is denoted by K. So we can say K is equal to normal stress upon volumetric strain. When a body is immersed in a fluid or liquid, then the modulus of modulus, that is the elastic constant that will develop in the material, that will be your bulk modulus. Now modulus of rigidity or shear modulus, it is defined as the ratio of shear stress to shear strain, and is denoted by G or C. In some books it is denoted by G, and in other books it is denoted by C. So we can say C or G is equal to shear stress upon shear strain. So these three modulus of elasticity and bulk modulus, modulus of rigidity, these are the material property, and it is constant for a particular material. Now, this is a very important concept, true stress and engineering stress. Now, what is engineering stress? Engineering stress, see, I have written sigma engineering is equal to P upon A naught. And what is this A naught? A naught is the original cross-sectional area. P is the applied load. So, engineering stress is defined as the ratio of applied load to the original cross-sectional area A naught. Also, it is called as nominal stress. Then true stress, I have written sigma TR, P upon A. It is defined as the ratio of applied load P to the instantaneous or actual cross-sectional area. Now, what is that actual area and the original area? You see, in the first diagram, there is a body is there, and the cross-sectional area I have given is A naught, and this is the original cross-sectional area, means this is the body, and in that body I'm applying a load P, tensile load, applying a tensile load. Now after the application of the load, the deformation will be like this. So the cross-section will be decreased. Cross-section will be decreased. So I have written here A is the actual cross-sectional area, that is after the application of the load. So the stress developed after the application of the load with the actual cross-sectional area is called the true stress. That is sigma TR is equal to P upon A, where A is the actual cross-sectional area, and P upon A naught is the sigma engineering stress. It is normally load upon the original cross-sectional area. So these are the difference between engineering stress and the true stress. Similarly, there are engineering strain also and true strain also. Now look at this figure. See, there is a body whose original length is L0 and you are applying a tensile load along the y-axis. Now after the application of the load, what will happen? The L0 will be increased to dl, L0 plus dl. Means dl is the elongation, you can say the elongation, or it is the change in length after the application of the axial load along y-axis. Then total length, that is the actual length, will be L0 plus dl. Actual length will be L0 plus dl, that is after the application of the load. So engineering strain can be defined as the ratio of the change in dimension to the original dimension, dl upon L0. L0 is the original dimension. And true strain is defined as the ratio of natural log of actual length. Actual length is L. Actual length is L0 plus dl to the original length. Original length is L0. So ln L by L0 is the true strain. And what is L? L is the summation of the change in length and the original length. Now, I am showing the relation between the true stress and engineering stress, and also true strain and engineering strain. Now let us consider P is equal to applied load, N0 is the original area, A is the actual area. So we can easily find out the engineering stress is equal to load upon original area and true stress is equal to load upon actual area. Again, if dl is the change in length, L0 is the original length, L is the actual length. So actual length is equal to change in length plus original length. So we can say engineering strain is equal to change in length to the original length, and true strain is equal to logarithm, that is the natural logarithm of L, means actual length to the original length. Also we know that from the continuity equation, area multiplied by length is the volume, and area multiplied by length is also volume. So volume will remain constant. So N0 L0 is equal to AL. We will use this equation here. See, this is sigma TR, that is the true stress, is equal to P upon A. Okay. So P L N0 L0. From where it is coming? See, if I want to replace this A, so from this equation, A is equal to N0 L0 divided by L. So I put N0 L0 and take L in the up. So it is PL divided by N0 L0. So this is equal to P0 upon N0, P upon N0, load upon original area multiplied by L, that is the actual length, divided by the original length. So P upon N0, that is the load upon original area, is the engineering stress. So I put it here sigma engineering. And L can be written as DL plus L0 divided by the L0. Now what will happen? Sigma TR, true stress, is equal to sigma engineering into here L0 by L0. It will 1 and DL by L0. So 1 plus DL by L0. And what is DL by L0? See, DL by L0 is the engineering strain. Engineering strain. So ultimately I am getting sigma TR, true stress, is equal to sigma engineering stress multiplied by 1 plus engineering strain. So this is the relation between true stress and engineering stress. That is the relation between true stress and the engineering stress. Now see, this is sigma TR. Sigma TR means, ETR means true strain. ETR means true strain. So true strain is equal to natural log of L upon L0. L is the actual length. So I put actual length as DL plus L0 divided by L0. So ln 1 plus DL by L0. So ln 1 plus DL by L0 is engineering strain. So I got true strain is equal to natural logarithm of 1 plus engineering strain. This is the relation. So these two relations you have to remember The sigma TR, that is the true stress, is equal to engineering stress multiplied by 1 plus engineering strain, and in true strain is equal to natural logarithm of 1 plus engineering strain. Okay. Now there is a small derivation, that is the total elongation produced in a uniform circular bar under external load. Means there is a uniform bar. Let us consider circular body of length L and cross-sectional area A is fixed at one end, fixed. In the top end it is fixed. An external load P is acting at the other end. At the other end, external load P is acting, as shown in the figure. Now upon the application of the load, there will be extension of the length, and the extension of the length I have taken as DL because of the load P, and let us assume E is the Young's modulus of the material. Now what? See, we know the stress is equal to load upon area, so it is P upon A, and strain E is equal to change in length DL divided by the original length L. From Hooke's law, we know stress is equal to some constant into strain. Since here linear stress is there, linear strain is there, so the K will be your Young's modulus, because Young's modulus is defined as the ratio of linear stress to the linear strain. So I can write sigma is equal to E, capital E into small e. And what is sigma? It is load upon area, P upon A. E, and what is E? Strain, change in length by original length. So if I do the cross multiplication, I will get DL is equal to PL upon A. So this is the total elongation produced in a uniform circular bar under the external load. DL is equal to PL upon A, where P is the applied load, L is the length, original length, A is the cross-sectional area, E is the Young's modulus. If diameter is given, then you can find out the area pi by 4 d square. So with this, I have completed today's lecture. If you find my video good enough for you, then please share it, subscribe it. This is my email ID. If you have any queries, you can contact through mail. So thank you very much.